This portion of chapter 2 is going to cover acids and bases. Right here we see examples of naturally occurring acids. This is citric acid, which is found in our citrus fruits. And then in our cleaning reagent, we have compounds that are mostly bases. So we have in Windex, we have ammonia. And then in soaps, we usually have sodium hydroxide. Here are a few more examples of acids and bases. So here we can see acetic acid, which is a common acid in vinegar. We have HCl, which is found in our stomach. And then we have sulfuric acid, which is usually found in car batteries. Now, acids and bases can be classified either as organic or inorganic acids. So what are organic acids and what are inorganic acids? Basically, organic acids contain the element carbon. We've already defined what organic chemistry is. The definition is compounds that contain carbon in their structures. So here in acetic acid, you can see the carbons are on these positions. And then we have another compound which is called benzoic acid. Now if you're doing 3100 lab, you should have already started using benzoic acid, which was one of the compounds you used in experiment 1. So we're going to learn later on how to draw structures of compounds. So here this is a carbon, that's a carbon, and so forth. Inorganic acids, of course, are those that do not contain carbon as part of their structures. So you can see examples include HCl, sulfuric acid, nitric acid, and phosphoric acid. All these do not have carbon in their structure. Organic bases, again, they're bases, but since they're organic, they should contain the carbon element. Whereas inorganic bases, as listed here, they do not contain your carbon atom. Now, acids and bases have been defined in different ways. We have 3 definitions. We have the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis acid definition. Why do we have so many different definitions for acids and bases? The reason is when they first discovered acids and bases, they started with a basic definition of acids and bases. So an acid in terms of the Arrhenius definition, an Arrhenius acid is a substance that releases hydrogen ions, that is H+, when it's in solution. Whereas an Arrhenius base is a substance that releases hydroxide ions, that is OH- when in solution. So this definition was very limited because it only applied to only those compounds that when they were placed in solution, they would have to release an H+. If it's a base and it's placed in solution, then it should release OH-. But as time went by, they realized that there were other compounds that were not able to release an H+ or an OH-, so they had to broaden the definition. Hence the reason we have the Bronsted-Lowry definition, which again was kind of limited, so that's why they came up with the Lewis definition of acids and bases, which encompasses all kinds of acids. So in terms of the Bronsted-Lowry definition, your acids are basically substances that donate a hydrogen ion, whereas your Bronsted bases accept hydrogen ions. So below is an example of an acid-base reaction, and we're going to use the curved arrow formalism to show the movement of electrons. This curved arrow shows where electrons are moving from and where they're going to, and then you should be able, by the end of this chapter, you're going to be able to know how to use the curved arrow formalism and then to come up with the structures of the products that are formed from an acid-base reaction. So normally, and I want you guys to get this from the start, you always move your arrow from the base to the acid. Again, the arrow always moves from the base to the acid. So we're going to use this arrow. So here, your bases, you can identify bases mainly if you have nitrogen containing compounds. Generally, they're identified as bases. Or bases can also be identified if a compound contains lone pair of electrons, like we see in this compound here. So we're going to move an arrow from the base to the acid. So remember, acids donate a proton. So it's this proton that's going to be donated to the base, and then the base is going to accept the proton. So if you use the curved arrow formalism, remember it moves from the base to the acid. Okay, so then once you move the arrow here, this bond is going to break to the oxygen. And the reason why you don't just stop by putting the arrow here, remember hydrogen is in group 1. It only forms one bond so that it can become like helium. So if I stop here, it means hydrogen is going to have 2 bonds. So this is why this bond has to break so that these electrons can go to the oxygen. So when that happens, then you can see that the electrons, these electrons here came from this bond here. So the oxygen now gains a negative charge. Nitrogen has used its lone pair of electrons. So then it's electron poor. So then again, if you look at the product here, nitrogen was already attached to 3 hydrogens. So now it has 4 hydrogens. That means it's forming 4 bonds. And remember, nitrogen is only allowed to form 3 bonds. So if it has an abnormal number of bonds, then it has to carry a formal charge. So the plus charge here is due to a formal charge. But one way that you can remember this, what charges do you put where? If you break a bond, the electrons, if they move to an atom, that atom gains a negative charge. If you lose a lone pair of electrons, that atom will gain a positive charge. So this is an acid, this is a base. The compound in your product which contains your negative charge is called the conjugate base. If it contains a plus charge, this is always referred to as a conjugate acid. So you need to know the terms. You need to be able to, if you're given a reaction, you need to be able to identify what is an acid, what's a base, what's a conjugate base, and what's a conjugate acid.